So we've looked at the units for charge, so we've now got the charge of the electron in coulombs. What we've got to look at now is try to formalise that for the other parts of atoms. So just a quick reminder about what atoms are made from and how we represent them. Most of that should be revision from GCSE knowledge. And we need to just formalise the properties of the particles, the three particles that atoms are made from. Okay, just to start us off, think about a helium-4 atom, how we can draw it. This should be fairly straightforward to us. We've got protons and neutrons in the middle. We've got electrons. These electrons are going around in the first shell. Sure, in chemistry you'll have said only 2 electrons can fit in the first shell. We'll talk about how those electrons go much more later on. So we've got the electrons going around the outside. We've got this whole thing in the middle, the nucleus. We've got protons and neutrons. If any of that's a surprise to you, then you might be in a bit of trouble. So hopefully that's pretty straightforward. Things that are wrong with this model, well, the nucleus for one thing is far too big. Okay, to scale, the nucleus is only about 10 to the minus 15, something times 10 to the minus 15 metres across. The atom something around 10 to the minus 10 metres across, so 100,000 times bigger. Okay, you can't really draw these things to scale, otherwise the nucleus would just be a single tiny dot in the middle. Whether the electrons can really be represented as little points going round is another interesting question we'll come back to later in the module. So there's a few things wrong with that, but it's a good enough working model for us to have in our minds at the moment. Okay, I'm sure you'll be familiar with this from GCSE. So this is how we write an atomic nucleus. So we've got a mass number at the top. This is the number of protons and neutrons added together. An atomic number at the bottom, just the number of protons, and a symbol here. Sometimes this symbol, this number is missing because if it's carbon, it must be 6. You can't have 7 there and have C there, or have C there and have a different number than 6 here. Okay, if there's 6 protons, it's carbon. Okay, it should mention here that it's the number of protons that defines what element it is. Sometimes people think from GCSE it's the number of electrons, but if I take an electron off, I've still got a carbon nucleus. So the protons, the atomic number, tells you what element it is. Okay, this should be fairly straightforward. So here's hydrogen 1. Just have to be careful. This is 1 proton, 1 nucleon. So here's a new word maybe to us. A nucleon is a particle in a nucleus. So this is just protons and neutrons added together. So 1 proton, 1 nucleon means there must be no neutrons. Okay, you can run through those quite straightforwardly. Really the only trap here is just to make sure that if you're asked for the number of neutrons, you're doing the difference between the number of protons and the number of nucleons. Okay, so you'll have done this table at GCSE. This is relative masses and charges. Okay, we've already said that we know the relative charge of the electron, and we've tried to move on to the actual charge in coulombs. Well, we need to do the same thing for the masses. We know the relative masses of protons and neutrons and electrons, but what we need to know is their actual mass in kilograms. So hopefully you're fairly confident with this. Relative mass of a proton is 1. Relative charge is 1. We just write +1 just to remind ourselves it's positive. Relative mass of the neutron is 1. Relative charge is 0. Relative mass of the electron, you might have written very small there, or 1 over 2,000, or 1 over 1,860. We're now going to say that that's relative to the ones that's 0.00055. Okay, so that's roughly 1/2000th, slightly more accurately 1/1860th. Relative charge, -1. Okay, this makes it look as if protons and neutrons have got the same mass, which if we round it off they have, but in fact neutrons are a little bit heavier, so these are not exact numbers. Okay, these are not exactly the same mass, they are quite close. These are exactly the same charge, just with opposite signs. So here's the tricky bit in this lesson. What we need to do is to try to work out these masses, not relative to each other, but actually in kilograms. So we've mentioned before that 1 mole is 6 times 10 to 23 atoms, and that's that number comes from the idea that 1 mole of carbon-12 atoms has got a mass of 12 grams. So this is really important in chemistry. 1 mole of carbon-12 atoms has got a mass of 12 grams. But we can work out the mass of a carbon-12 atom in relative units, okay, which we call U, because a carbon-12 atom is made from 6 protons, 6 neutrons and 6 electrons. So we've got 6 lots of 1U for the protons, 6 lots of 1U for the neutrons, and 6 lots of 0.00055U for the electrons. Okay, that gives us this. We can just round that off near enough to 12U, bearing in mind that these aren't exactly 1 in the first place. Okay, so even to 4 significant figures, 12.00U. So one atom of carbon has got a relative mass of 12U. Okay, in relative units, 1 mole, well 1 mole is this number of those atoms, one of them weighs this much. So we've got 12U times this number of atoms, so that's 7.2 times 10 to the 24U. Okay, but we also know that's 12 grams. Chemists like to use grams. We're proper scientists, so we like to use kilograms. So 0.012 kilograms is the same thing as 7.2 times 10 to the 24U. Okay, a little conversion there tells us that 1U must be 0.012 divided by this 7.2 times 10 to the 24, 1.66 times 10 to the minus 27 kilograms. So when we say the relative mass of is 1U, okay, the actual mass in kilograms is 1.66 times 10 to the minus 27 kilograms. We can do that for electrons as well, because we've already said that an electron is 0.00055U. So all we've got to do is multiply that by what 1U is, and we find the mass of the electron is 9.1 times 10 to the minus 31 kilograms. Okay, so let's go back to our same table. Okay, this table looks the same. Okay, but in fact, you'll notice here this doesn't say relative mass and relative charge anymore. This is mass in kilograms, charge in coulombs. Okay, so if you're asked for the mass of a proton now, or the charge of an electron, don't put +1 and -1. Okay, we need some actual units. So proton's got a mass of 1.66 times 10 to the minus 27, and a neutron is the same to 3 significant figures, just slightly higher actually. There's the electron. The charge, as we know from the previous lesson, proton 1.6 times 10 to the minus 19, neutron of course exactly 0, and the electron same as the proton but with the opposite sign. Okay, so all the stuff that we're going to do in the future, it's really important that you're clear on these numbers, the actual masses and charges in kilograms and coulombs, okay, so that we can actually work out some proper numbers rather than just what they are relative to each other.